Office, telephone number. So these are all not applicable anymore. So, so basically, what I think what we're going to touch today, this 1 hour, let's see how far we are. We will try to cover the basics as much as possible. This is for the advanced use, but we may or may not be discussing about this. But okay, this I think we can skip. Yeah. So basically, what we have for, say, for example, yeah, we have a plant. So we have this plant, like in this script or whatnot. So we have yeah, columns, reboiler, reactor 1, reactor 2, and so on. So we have exchangers as well. So we have 1, 2, 3, 4, 5 exchangers, 6 reboiler with condenser, and then 7 with the reboiler. So basically, so let's see. So we have a feed coming at 80 degrees C, and then we know what the flow is, and then it goes to the first exchanger, and then there's the where the temperature is heated from 80 degrees C to 102.5 degrees C, and then there is a heater to increase the temperature from 102 to 140 degrees C, and then it is mixed with another stream, gets into the reactor 1. And then the same goes with the reactor 2. It has exothermic reaction, and then the 170 degrees C, and then we need to cool it down to 60 degrees C before it can enter the column. And then from this column, we have a condenser. And then this condenser is cooled somehow, yeah, somehow at until 20 degrees C, and then this 20 degrees C, sorry, being heated up by the stream coming from the reactor. And then it goes to it reaches 135 degrees C, goes back to reactor 1, and so on and so forth. And then the bottom product goes to the basically it's being cooled down with this feed, and then it's being cooled down further to 30 degrees C, goes to somewhere else. So basically we have like 1, 2, 3, 4, 5 exchanges that we can do something about. We have the stream data. I think you know already by now that we need to have the stream the stream flow rate, and then we need to have the temperature data around the exchanger, and then we need to have also the duty, or yeah, if we know what the MCP is of the streams, then we can calculate the duty accordingly. If we don't know what the MCP is, and then if we know the duty, and then we can also calculate MCP accordingly. If we know we need to know the temperature. That's number 1 rule. So basically, so that's typical the data extraction that we are taking from the plant. I think it's the same as well with how the, let me know, yeah, if you have any questions, let me know, and then just shoot. And then if it feels different than what this KPR is doing, also let me know, so then we can also learn from them how to do this from their perspective. So this is then basically what it is about the process, yeah. And then the number 1 issue in all of this heat exchange or this pinch analysis stuff is that we need to get the data correctly, because we are going to use this data in such a way that it will become like our current situation evaluation, as well as the target or the benchmark. So we have a current situations, so that we know the current situation means we know we have our heater heated from the steam, and then we have another heater. Sorry, we have one heater, and then we have it's a cooler, and that's another cooler. So we have one heater and then two coolers. So our steam system, for example, yeah, it's supply. We need to have 150 kilowatt from the steam, and then we are going to destroy 190 to the cooling water. Yeah, 190 kilowatt to cooling water, and then 150 kilowatt from the steam. So we have our existing heating and cooling utilities using this schematic plant. And then we are exchanging 230 kilowatt and then 90 kilowatt of heat. So this is then the heat that we are exchanging. This is the heat that we are getting from the outside. So this is basically the current situations. Now we know the current situations. We need to know what we can do further to improve this situation. That's basically what the answer that this pinch is going to address. But before we do that, we need to know how to get the data correctly. So in principle, how to get the data correctly is that we need to know the beginning and the end. For example, this stream this stream is coming at 80 degrees C. So we can ask ourselves, why is this 80 degrees C? Right? If it's coming from the storage, it should be like a room temperature, for example. If it's coming from another place, and then that we need to understand why it is 80 degrees C. Can we increase this further, or is it something that it can be reduced? So these numbers, all of these temperature numbers, we have to question them for everything, why they are the way they are. Say that these are like a fixed number, yeah, we don't know, and then we are not allowed to ask, I don't know. This is going to be heated from 80 degrees C, and then to how much is going to be heated. So we have one stream at 102 and another one at 140. This is coming at 135. So basically, what is then the temperature range, or what kind of data that we need to extract from this stream, basically? Yeah. Or is it this stream only, or is it then this stream until that one, or is it from here until that one? So the general rule is that we need to know the beginning and the end. So beginning is coming at 80 degrees C, and then the end is the end is that the unit operation that requires a certain condition to be fulfilled. For example, yeah, this exchanger, for example, this heater, does it need to have incoming of 120 102 degrees C? This heater, it doesn't care much. Yeah, what we can see from here is that this reactor can only, or this reaction can only occur at 140 135 degrees C, for example. So in that sense, if this is then 140 degrees C, we can say that this stream is going to be heated from 80 degrees C to 140 degrees C. Yeah, from 80 to 140 degrees C. So this stream is going to be all the way from this beginning until the end. So 80 to 140 degrees C, and then how much energy that we have to supply is this number, 150 plus 90. So 240 kilowatt is then the amount of energy that we need to supply for this stream to be able to increase the temperature from 80 to 140 degrees C. So this is then our stream number 1. As a cold stream. Yeah, cold stream, we define it as cold stream because we need to increase the temperature. And then let's see this stream, for example. This stream is coming from the R2, and then it has 170 degrees C, and then it needs to be cooled down to this, basically these conditions. So the next unit operations is not these two heaters or two exchanges, but this column. It needs to have 60 degrees C, and then we can also question ourselves, does it need to be 60 degrees C? Can it be lower? Can it be higher? So these numbers, we have to make sure that we understand the reason behind them, so that we can then extract the correct number. So say, for example, this is given at 170 degrees C because of the reaction constraint, for example, and this then because of the flash within the column that we need to have. So we stick with 170 to 60 degrees C, and then we want to cool it down from 170 to 60 degrees C. This is then the amount of energy that we need to remove from it. So 330 kilowatts. Inlet temperature, outlet temperature, and then we can calculate also the MCP. Yeah? So this is then stream number 2. And then also stream number 3, for example, from here. So we know that we have a stream coming on 20 degrees C somehow, and then we now it's coming out, or it's entering the reactor 1 at 135 degrees C. So we can keep it this way. Yeah. We can also question why 135, why not 140, or why not 130, something like that. So we can question that one, but say for the sake of this exercise, it's 135. So this is then another stream. So again, this is then the cold stream needs to be heated. This is then hot stream because it needs to be cooled down, and this is also a cold stream because it needs to be heated. And the last stream is then this stream, 150 degrees C. It needs to be cooled down to 30 degrees C. So this means because this stream needs to be cooled down, it is then a hot stream. So we have one cold stream, and then two cold streams, and then we have one hot stream, and then two hot streams. So we have two hot streams, two cold streams. Yeah. Up until this, is there any question?
Not from me.
Yeah. Jessica, no.
No question.
Yeah. So I think to emphasize it again, number one is that we need to understand what the process that we are dealing with, its current conditions, and then the data that we want to extract. So that's then the theoretical part. But then practically, do we need to consider as well? Because now we can see theoretically we have like two hot stream, two cold streams. But in practice, do we need to consider all of these two hot stream and two cold streams? That depends. That depends. Yeah, that depends on how much is then the energy that we are exchanging. For example, these streams we need to exchange 240 kilowatts. These streams we need to add 330 kilowatt. We need to remove, and this stream is 230 kilowatts, and this stream is 180 kilowatt. Are these like numbers that we can exchange? I mean, are they worthy of being evaluated? That's the question that we have to ask ourselves. If for example, if this is then like 1 kilowatt or maybe 5 kilowatt, so we don't need to bother with this. I mean, if this 1 kilowatt or 5 kilowatt compared to this 90, this 100, 200, 300, so this 5, 10 kilowatt, it means nothing. It's peanuts. So in that sense, for practical reasons, we can just remove this. And then we can say that this stream is going to be a cool down from 150 to 90 degrees C, for example. Yeah. And then if there is any reasons to keep it at 90 degrees C, so that means it's even we can even neglect this exchanger, for example. And yeah.
Alina.
Oh
Sorry.
yeah.
So kalau if you mention this is at the early stage of the designing, right?
No. It
And
is existing.
existing. Oh, okay.
Existing.
Oh, existing. So memang we just evaluating from the existing lah.
Yeah, betul.
If but if it is in design stage, we don't even have this SNG, right?
Betul.
So
Tak ada.
our main line is actually only the main yang you cakap lah, stream number one to the
Betul.
reactors and
Yeah.
to the column, right?
Yeah.
So later baru we put in the heat
Yes.
exchangers.
Yeah.
But now we evaluating the existing.
So
Okay.
this existing, we can see that the two exchanges are like exchanging heat, and then the one heater, two coolers. But in design, we don't start with this. What we have is then typically we start from 80 degrees C to 140 degrees C. So we have one big exchanger only. And then this also like we have another big exchanger, and then this one is also another big exchanger, and this also another big exchanger. So we have like 4 exchanges, heaters and coolers, to get the duty done, to get the duties done correctly. But in this, because this is like existing, so we have like already 2 exchanging heat somehow.
Okay.
Okay. Any other questions? No. This one you will see that later. So this is then I think I don't know if we have to go through this concept, but in any case I will explain on this graph, because this then the graph that is going to be, that's going to come every now and then in this pinch analysis. So we have this temperature y-axis and then energy or enthalpy or duty or whatnot on the x-axis. So if we say that we have a hot stream, that means hot stream is then the stream that needs to be cooled down. So temperature goes from here to there. So it's so this T1 is then higher than this T2, means we are reducing the temperature, means this is then a hot stream. The same goes with the cold streams. You want to increase the temperature from here to there. So if I put them all overlapping on the x-axis, overlapping on the x-axis, so we can see that we can then transfer this amount of energy from this stream to this stream, basically. So we can then exchange the heat between them. So that's basically what it is. And then MCP delta T is then one formula that we have to put in mind. And then another formula is then the amount of energy being exchanged in a heat exchanger, UA delta T, LMTD. Yeah, don't forget about the LMTD. So that's the so we come back with these flow sheets, and then we know that we have already the we know what are the streams that needs to be cooled and hot and heated. So we can then see it in a different way. So this is then stream needs to be cooled down. So 180 kilowatt is then this 90 plus 90, 180. It needs to be cooled down from 150 to 30 degrees C. This guy is also from 80 to 140 degrees C. This one big exchanger. So 90 plus 150 makes 240. And then we can calculate the MCP. This CP is then MCP, 4 kilowatt per degree C. So this is basically the data that we are going to extract from this flow sheet. This is also continuing from Zelina's questions. This is then basically if we start from scratch, I mean from design, this is what we typically end up with. So we want to hit this to reactor, this one to be cooled down, this one to be heated up, and this one to be cooled down. So this is typically what we have in the design phase.
Yep.
Yeah. So we come back to design. So this is then the typical data that we are going to get. So we put them into this stream. So this is then the Excel file that KBR shared. So they put this cold and hot they code it somehow based on the temperature that we put in. So if, for example, stream one, I don't remember. Stream one is then from 20 degrees C to 135. So this is then the stream one. From 20 to 135, and then the amount of energy that we are exchanging is then 230 kilowatt. So this is then the 230 kilowatt, and then the MCP or the flow is then the heat flow is then 2. So this is then this divided by delta T. Yeah. So 230 divided by delta T, we get kilowatt per degree C, which is 2. The same goes with the other streams as well. So 170 to 60, 170 to 60, 80 to 140, 80 to 140, 150 to 30. So we know the loads, and then we know we can then calculate the flow. So this is then the Excel sheet that KBR is sharing with us basically. These data extractions, I will just skip this for the time being. Yeah. Basically, how much time now? Oh, I can spend 5 minutes here. So because data extraction is very important. Coming back to that, if we have a very small streams, should we include that or not? And then practically the answer is not. And then there was a question as well, I think some 10 years ago. So depending on the sites, what is then the threshold then to consider whether a stream can be included in the analysis or not? Yeah. That really depends on the site. In some sites, it's like in the order of kilowatts, it's good. It's considered as a big stream. But in other sites, if it's in the order of megawatt, then it is considered as a big stream. So it really depends on the sites that we are dealing with. So so we need to really understand. So that's I'm emphasizing the point that we really need to understand the situations of our plant. So we need to understand the plant. The linearizations, that is not for us at the time, for the time being. The other rule is that do not mix streams. For example, we have one stream coming here and another stream coming there, and then they are all mixed in here. So the general rule is that we cannot treat this as one stream, and then one stream, making it 3 streams, but we should treat them as 2 separate streams. So this one stream is then cooled down from 150 to 30 degrees C, because we know the flow rate, right? We know the flow rate, we know the CP, we can calculate the MCP, and then we know the temperature coming in, we know the target temperature, we can calculate the amount of duty that we need to remove from here to there. So this is one stream, that's one stream. So this is then the general rule. Yeah. Why we are not recommended to mix streams? Because this mixed stream is I don't know how they mix or how to call it. We don't know why they are being mixed. Yeah. If it's only like if we know exactly the reason why they are being mixed, fine. But if we don't know, I mean, there is no reason. If there is no reason why they are being mixed other than, I don't know, we don't know. So it's better to separate them so that we do not lose any opportunity in the heat recovery later on. The other extraction rule is that do not extract utilities, means because this is going to be designed, means that we are considering the stream from here to there. Yeah, not from here to there, and then not from here to there. So if we need to look this stream as one big stream from one location to the other locations. This has a requirement that has a requirement, yeah, so which we cannot violate. So this we can consider like one stream. So we cannot use that. We cannot define this stream as from here to there. So this is one stream, and then from here to there, that's another stream. So it's not recommended to do so, because then if we do so, that means we will not be able to see any improvement later on. We will see this mistake later on. That is this one. And then extract effective temperature means it's this exchanger. It is then being used to produce steam, and then it's using this to 377 until 375 degrees C, basically. So this temperature, we need to consider, are they really the true temperature or not? Yeah. So and then are they, like, for example, in this particular case, um, so this 377, it seems like 377s, but then this whole thing, if we can see this reactor, it's we can safely assume, that at because this is like a because the feed is the reactant is going through the tubes, and this is then the molten salt is going around, and then this reactor feed is then the the reactants is then it has an exothermic reactor reaction, so 127 to 3075 degrees C, and then it's being then cooled down, yeah, by this molten salt. So this molten salt is coming at 375 degrees C, and then somehow it ends up with 377 degrees C. So we need to ask ourselves, is this really true or not? Yeah, because we are going to use this to produce steam anyway. So it is then better to say that we are having like 375 degrees C, and then we have like a delta T, very small delta T, like 1 degree C, and then we will then use the amount of energy to produce steam. So this 377 degrees C, basically in this particular case, we cannot see it literally as 377 degrees C. We can see it as well as 375 degrees C. Yeah, to make sure that we are on the safe side when we want to do some heat recovery later on. And then soft data. Soft data means that 80 degrees C example. So it goes to the tank at 80 degrees C, but then we can question ourselves: does it need to be really 80 degrees C? Can we reduce it somehow so that we can recover the heat more, or there's a constraint? Yeah. Why not 30 degrees C, for example, in this case? Because then we can then extract more heat from this stream. So that's basically what this is. What this means by the soft data. For hard data, that is then the reactor conditions typically, and then distillation columns conditions. These are typically the hard data that we it's very difficult for us to navigate around this. But for storage tank, for other type of situations other than the reactors, typically we can question ourselves whether the data mentioned are hard or soft. Composite curve, I think we can skip this on how to do this, yeah, because we have the KBR, we have the KBR Excel file, and then there are plenty of tools on how to make the curve. But I would like to show you is that in our examples, we have 2 hot streams and then 2 cold streams, yeah. And then the 2 cold streams are merged into one curve we call cold composite curve, and then the 2 hot streams are merged into one big curve called hot composite curve. So if we put them, we'll have these two hot stream, and then when we merge them, it becomes this line. Yeah, so I will skip on how to do this in detail because there are tools already doing it for us. So basically, we have this then hot streams, and this is then the cold streams. So this is my old Excel, which where I did this. So we have one cold composite curve and then the hot composite curve. Again, hot composite curve comes from hot streams that needs to be cooled down, and then cold composite curve comes from the cold stream that needs to be heated up.
So fun.
Yeah.
Like this one, we know that the system is quite big, quite small. So you have only two. But when you evaluating the actual plan, right? So are you cutting your plan to according to unit so that you have less number to be combined, or memang you buat the
Memang
whole thing and
memang buat the
combine
whole thing.
semua?
Memang buat the
So
whole thing.
so you have 10 cold
We have
stream, then I don't know,
dozens.
banyak sangat.
Betul.
Then you just combine terus lah.
Betul. So this can be it can look whatever. Yeah, I think I have the slides later on. So it can look whatever. So depends highly on the plans that we are dealing with.
Oh, and only one lah. You
Only one.
anyhow you have to combine.
Yeah. Anyone. So
Okay.
this can be like a combination of 2 streams, 3 streams, or even 1,000 streams. This one is also 1,000, 1,000,000 streams. It's up to us.
All right.
So there are 3 concepts here. Temperature is fixed, yeah, because temperature are process requirements. Yeah, once we know that these the temperatures are how they should be, so we keep them constant. Yeah, because they are hard constraints. We cannot deal with that anymore. So this curve is there, and then that curve is there. This pinch point, so hence the term pinch, is then the area where the 2 curves are at the smallest distance. Yeah, I repeat, the pinch point is then the area, the point at which the 2 curves are located as close at the closest point. So if we can see it here from the temperature perspective, we can see from this one, this temperature is 20 degrees C. That temperature is about, I don't know, 70 something. So 70 something minus 20, it's about 50 something. So this one as well, 680 minus like 40, it's about 40. So this whole delta T we can then calculate, and so on and so forth, and then we can see in this graph, in this graph particularly, we have this as the smallest distance, 20 degrees C. 100 minus 80. So this 20 degrees C, at this case is what we call our delta T mean, or the pinch, delta T pinch, or whatever they want to call it, delta T mean basically. So delta T mean. So this, if we have a delta T mean of 20 degrees C, so this is then the positions of the 2 curves. So 20 degrees C is then at the lowest, is then the shortest distance between these 2 curves. And this 20 degrees C happens to be like 100 degrees C at the hot composite curve, and then 80 degrees C at the cold composite curve. So we have 100 degrees C over there, hot pinch, and then 80 degrees C, cold pinch. But then the temperature pinch itself, people normally take the somewhere in the middle, the 90 degrees C. Why is that? I will show you later on. But then again, the concept is then the pinch temperature is then the temperature at which the 2 curves are at the closest. So if we allow them to be as close as 20 degrees C, this is going to be the results. So this 20 degrees C, or the delta T mean selection, is important. I think that Jem guy from KBR has mentioned like for 3 different delta T, what the impact is. But we will see that later on. We have 2 curves, delta T, pinch temperature is covered, and then the 2 curves here, the area, they are non-overlapping area. There is also an overlapping area until here, overlapping area. If we see from the heat load perspective, the enthalpy perspective, these are then the overlapping. This is non-overlapping, but the hot composite curve is not overlapped. This area is then the cold composite curve is not overlapped. So in this case, this cold composite curve, sorry, I will start with the heat graph. So this overlapping space means we have enough heat from the hot streams to hit the cold streams. So everything here, like what I showed you here, this is then the overlapping area. So we have all the heat coming from the hot streams can be used to heat up the cold streams. So that's basically what this is, the overlapping area. So all of this heat can be used to heat up the cold streams. But then the area where there is non-overlapping, like in this area, so these cold streams, it doesn't have the hot stream to be to be supplied with the energy with. So we need to have an external utility. So this then the amount So from this point to that point, so this is then the amount of heat that we need to supply to the plant so that this stream or this part of the plant can be fulfilled. So this distance, the x distance, is then the heating utility, the minimum heating utility. This is coming from our steam system or hot oil system, for example. So this is the minimum utility that we have to supply. We can supply more heat, but we cannot supply less heat than this because of this constraint. I will show you later on. The same goes with the cooling utility. So the area where the hot streams are not covered by the cold streams, so that means this heat, it has to go somewhere. This heat has to go somewhere. So this heat that has to go somewhere typically goes to the cooling tower, for example. So this is then the minimum cooling utility, 105 kilowatts. So 105 kilowatt. That goes to the cooling tower. So we are going to destroy this 105 kilowatt to the cooling tower. We can destroy more, but this is then the minimum that we can destroy. We cannot destroy less than this theoretically. Okay. So until now we have covered the temperature pinch, the minimum heating utility, and then minimum cooling utility. Up until here, is there any question?
What is the significance of the temperature pinch 90 degrees though?
Yeah, exactly. So this is then the significance of that 90 degrees C. So basically this curve, the blue curve, for easier visualization, this blue curve we can move it to the right and to the left. Yeah, if we move it to the right, that means the distance between the hot curve and then the cold curve, the distance becomes wider. Yeah, if we move it to the right, you can imagine it becomes wider. If we move it to the left, that means the delta T will become smaller. So if we move it to the right, the delta T becomes larger, and also these non-overlapping area becomes larger. Yeah, can you imagine that? If we move it to the right, if we move everything to the right, this non-overlapping becomes larger. That means we will need more heating utility, and we also need more cooling utility because we move everything to the right. So we will need more utilities, heating and cooling, but we will have a higher delta T. In the other words is that we will need more money to pay for our utilities, but then we will need to have a smaller exchanger to build because the delta T is going to be big. Remember that UA delta T LMTD. So if delta T is big, it means the A is going to be small. So we have to pay for the OPEX and then we have to pay for the CAPEX for the exchanger. So playing around with this delta T means a huge impact to the cost calculations. So I have this delta T, so 20 degrees C, and this is about, I don't know why this is 10, but it is touching. But this is also 30 degrees C, this is 40 degrees C. So we can see our initial case is 65 kilowatt, 105 kilowatt. If we increase the delta T, if we move it to the right, if I get to the 30 degrees C as the minimum somewhere here, so that means I will add from 65, I will need 110. From 105, I will need 150 kilowatts. Yeah, so this goes to cooling tower. That comes from the steam system. And then the amount of heat recovery is also like lower compared to this guy. The same goes if I put it to the left a little bit by 10 degrees C. So this graph is wrong. Yeah. So we are reducing the amount of heating utility. So instead of getting 65 from the steam level, from the steam header, sorry, we only need 20 kilowatt from the steam header. Yeah, so that's a huge save in a bracket, in a quote. So and also from cooling utility, instead of discharging 100 kilowatts to the cooling tower, we only discharge 60 kilowatt to the cooling tower. So we save money from here to there, but we need to make sure that the amount of energy that we mentioned here, it has to be recovered as much as possible. Otherwise, we will not be able to meet these two targets. Yeah, and then we know, because we have now a smaller delta T throughout this graph, that means we will end up with a smaller delta T for the exchanges that we are going to design, and then we will end with the higher, with a bigger size of exchanges because of this UA delta T. Okay, so in this case, yes, we win on the OPEX, but we lose on the CAPEX. This part, we we lose on the OPEX because we need to pay double. Yeah, we lose on the OPEX, but we win in the CAPEX. This is somehow in between. So depending on the price of the CAPEX, depending of the price of the OPEX, yeah, it is also like site dependent and also country dependent. So the optimum delta T is going to be like site specific. Yeah? So there is no such a thing as the optimum delta P for the whole world, but there is an optimum delta P for a specific site because cost really differentiate the whole thing.
Sorry, Zulfan, I might miss just now. I know that the delta T mean is the delta yang nearest from the
Yeah.
curve, right?
Uh-uh.
How do we get the temperature pinch tu?
Temperature pinch tu say for example ini 20 kan, I mean besar sikit. So this is then the shortest distance 20 degrees C. The hot pinch is 100 degrees C, we can see 100 degrees C. And then the cold pinch is 80 degrees C.
So the delta is 20. So
delta is 20 and then divided by 2 we get the temperature pinch of 90 degrees C. So that's the 90 is basically somewhere in between.
In between, temperature in between.
Betul. I think I better say it now. This is one representation. Yeah, this is one representation of how to get this curve. Another representation which makes this going to be, we can see then the pinch part, is that to make sure that the heat can go from the hot composite curve to the cold composite curve, they put like a buffer, for example. Buffer, yeah. So how the buffer looks like, if they say I want to set limit, that the 20 degrees C is my minimum delta T that I can allow in my site. Yeah, I can repeat. So I want to set limits so that I have at least 20 degrees C available for the heat to be transferred in my plant. So that 20 degrees C is the set that we set for ourselves. Temperature that mean that we set for ourselves. And how we do the buffer is that we reduce this whole delta T. We reduce the whole curve by delta T divided by 2. So if we say that 20 degrees C, 20 divided by 2 will be 10. So this whole temperature will have to reduce by 10. So it will be then lower by 10. So the way we do it is that we do it here. So this hot stream, we reduce by 10. So 170 to 160, 60 to 50, and this is 150 to 140. This is 220. The same goes with the cold stream. We need to increase the cold stream by delta T by 10 as well. So we go back to here, and then we increase this to 30, 145, 90, and then 150. So in using these two adjusted data, and then we can see at the same 90 degrees C, the two curves are met. So they meet these two curves. They meet at 90 degrees C. Hence, the pinch temperature is 90 degrees C. If you can imagine now. So this is then down by 10. This then go up by 10. So that 90 is then where the curve where the two curves meet. Yeah. Hence the pinch term. So this is then the various different scenarios. This is the ideal situations where we have heat recovery in between, and then the cooling utility to the cooling tower, heating utility from the steam system, for example. So we could have no steam requirement, no heat requirement, but we have a utility requirement. We could also have hot utility requirement, but no cooling utility. We could also have these situations, cold utility at low temperature, cold utility at higher temperature as well. Hot utility at lower, hot utility at higher temperature. Yeah, all of these scenarios and many more can be present in our plant. We could also have like more than one pinch point. So far we have only like one pinch. Yeah. One pinch point over here, one pinch point over there, one pinch point over here, one pinch point over there. But in some cases, we could also have like 2 pinch points. So from here and then there, and maybe 3 or 4 or 5, or maybe in LNG, if you see it in the LNG plant, It is not pinch point but pinch line. So the hot curves and then the cold curves, they are consistently having the same delta T throughout the curves. That's in the LNG typically in that multi-stream heat exchanger. Multi-sided.
And very small, right?
Betul. So this is then another way to look at it, the problem table algorithm. I will skip this. Yeah, because the tools is also should have this. To do the problem table algorithm, this is then where we have to adjust the temperature. So the hot stream is then reduced by half delta T. The cold stream is going to be increased by half delta T, the one that I just mentioned. Then we can do this problem table algorithm. And then from this, this is then the composite curve with adjusted temperature, the 90 degrees C, yeah, same 65 kilowatts, 105 kilowatt, but it's just like the hot stream is then down by 10, the cold stream is then up by 10, so they meet at the pinch point. So from this, we can get from the adjusted temperature and then problem table algorithm, we can get the grand composite curve. Okay, I think what time is it now? I think for this session we'll just I'll make a clarification on this grand composite curve and then we will end it for this session. We'll continue later on. So somehow this has been built, yeah, with that KBR tool or with Aspen or with other Excel tools. So we get our composite curve with adjusted temperature. We can also have the composite curve without the adjusted temperature, and we can have the grand composite curve. So these are all created automatically. Yeah, the slides are just to help us understand how it is being created. But now since we have already the tool, so we don't really care too much on how it is being created. Nonetheless, the superiority of this graph, the grand composite curve, it lies with the fact that we can then set the utility level. For example, this is the grand composite curve for the same system. We can see that 90 degrees C is then where the curve touch the heat equals to 0. Yeah, so this is then basically the pinch point. So it is the same pinch point over here from the composite curve, where the two curves meet each other, and then this is then where the curve meets with the heat load of 0. So this is then the same pinch point, and then this region over here from there, yeah, from this curve below the pinch point. So the region below the pinch point is then the region where we have to remove heat. The region where we have to remove heat. So if we then see from 0 until 105, it is then the same as this number, 105 kilowatts, the amount of energy that we have to remove to the cooling tower. So this number. And then the above the pinch, this is the pinch, above the pinch is then the amount of energy, 65, the amount of energy that we need from the steam system, for example. So 65 kilowatts. So this is basically the same 65 kilowatts over here. The question comes, if we have this, so for example, yeah, we need to have 65 kilowatts. So what is then the heating medium? Do we need to send like 10 bar steam over here, or do we need to send 20 bar steam to heat our process, or do we need to send maybe just hot water, yeah, 100 degrees C or 90 degrees C? Which utility levels that we need to supply our process with? Based on this composite curve, the answer is not really clear. It is clear on this GCC. For example, you can see if it's this area over here, is what we call as pockets. So the area where there is the area where it is being, how to call it, being covered by the two curves, that one and that one. So this overlapping area is what we call the pocket, and this then typically the area where the process can fulfill the heating requirement by themselves. Yeah, that means we do not need the how do you call it, the extra utility from the steam system, for example, because this area can be fulfilled from within the process. So what cannot be fulfilled within the process is the one that is not being covered, the one that is that has no pockets, or the one that not being covered basically. So this area from 130, I don't know, 135 or something. So from 135, from 90 degrees C until 135, these are then the areas that the process needs to be heated basically. So if the maximum is about 135 degrees C, and while we have like a 5-bar steam somewhere, which is 150 degrees C, we can just better use it, right? So in this case, so we could also use like a 4-bar steam, sorry, it's about 140 degrees C. So it's somewhere here. So that means we can use 4-bar steam. We can use 5-bar steam. We could also use 20-bar steam, 20-bar steam somewhere here, or 40-bar steam. But they are useless if we have this kind of process, because to make that higher steam, we need to pay more money. But in fact, we only need to have a heating medium capable of heating until 140 degrees C, for example, or 135 degrees C if we want to touch this. Yeah. So we can say, okay, now from the steam level, I only need to have a 4-bar steam at this line. So the steam will then condense and it will give us this amount of steam, 65 kilowatt. The same goes with the utility. So are we going to destroy all of this to the cooling tower? Yeah, we don't know. Say for example, because this is then 90 degrees C. So this 90 degrees C in some areas, they can then recover this heat to make hot water. So they can make hot water from 60 degrees C to 90 degrees C, for example. So they can use, so we can touch the whole line over here. Yeah. So 60 degrees C is somewhere there. So they can 72, 73 amount to 73 kilowatts. They can reuse it to make hot water, which then being used to, I don't know, office uses or whatnot. So we can have this as another heating medium somewhere, which we can export or whatnot. So at least we can generate 60 until 90 degrees C of hot water if there is a chance or there is an opportunity to do so. And then the rest we can then send it to the cooling tower. And then how about this amount of energy? So how about this amount of pocket? So this pocket is also like the heat can be the heat that needs to be removed here can be used to heat the stream that is coming down, that is over here. So this is then the one exchanging the area where the process can exchange by themselves. And then this and the area, so it is then 30 degrees C until 20 degrees C. So depending on our cooling tower system, I don't think this we can discharge to the cooling tower. So we can either discharge this heat to the chilled water or the refrigeration system, yeah, depending on what cooling utility that we need to have. But for sure, we need to discharge this heat somewhere, somehow. So basically, we can have this kind of configurations. We can have option 1 is then steam at 170 degrees C, 65 kilowatt. Yeah, 170 degrees C. We put it on the grand composite curve, it will become like 160 kilowatt. Or we can have like a cooling utility, chilled water from 5 degrees C until 80 degrees C, for example. Yeah, for example, to get this 105 kilowatt, we can have a different one, different temperature of a chilled water from 5 until 15 degrees C. Yeah. But in this case, we know if the delta T is small, that means the flow rate is going to be big, right? So it's MCP delta T. If the delta T is small, we need to have a huge amount of flow rate over here compared to this one. This is going to be like a much less amount of flow rate of chilled water. We could also have like this 150 degrees C steam, put it on the 140 degrees C, and we can have like a 2 different cooling system, cooling water, and then the chilled water. We could also have like we use this 150 degrees C steam over here. Yeah, put it on the grand composite curve, makes 140. And we say if somehow, okay, this is not enough, and then I can use also the the 3-bar steam over here. This we can make a hot water producer, cooling water, and then another chilled water. So with this, we can play around and we can create, or we can utilize the existing steam or utility levels as we would like to have it. I think this is the end. 6 minutes to go until to the next for this session. Yeah. Any questions so far? At least until this GCC.
So from this GCC, just to confirm my understanding,
Yeah.
From one heating to heat from 135 to 150 boleh pakai proses punya heating.
Betul.
Don't need external, right?
Betul. We will see
Okay.
that later ya. We will see that in the next sessions.
So means like
How?
yang perlu utility is just the one yang tak ada pocket lah.
Betul,
So
betul,
okay.
betul.
But to use what kind? Okay, I faham on the steam sector, faham get the lowest possible steam level lah kan
Yeah,
that
to be
that
as cheap,
thing.
as possible.
On the cooling side, cooling side tu macam tak faham sangat. I mean, so
Cooling.
it's boleh
Huh?
pilih lah. I mean, it's an option lah whether you want to use refrigerant ke, nak pakai cooling water ke.
Yeah, basically itu. Basically we need depending on this temperature as well ya. Kadang-kadang ya, this temperature is quite high. We can also generate steam here.
Generate steam by cooling down 90.
By cooling this. Say for example, this pinch is not 90, but this pinch is 130 for example ya. If this whole curve is up by some degree C, so instead of sending all of this heat to the cooling tower, we can generate steam.
Okay, if it's above 100 lah.
Depending on this pinch temperature. Hence, this pinch temperature is very important. In this particular case, we could also produce hot water from 60 to 80 degrees C, like 40 kilowatt of hot water, and this as an option. And then this part we can send it to the cooling tower, and then this part unfortunately cooling tower cannot do so, so we have to send it to the chilled water, for example. If we don't want to have it, or if we say that it's 40 kilowatt is very small, for example, yeah, it's 40 kilowatt is very small, and then also not going to be a significant amount of it's not going to be like a profitable, for example, so we just better send all of this to cooling tower. That can also be a scenario. Yeah, so depending on the temperature level, depending on the how much energy that is available for us, we can say quickly whether it is feasible or not feasible. So this curve is just to guide us whether how many options can we generate, and then how we can then see which options can we bring forward, which options can we delete. This curve can help us to do so.
Baru faham sikit di sini. Tengok yang
betul.
I was confused macam what I'm looking at.
betul. Ini yang dia tak explain.
Dia kena explain this one kan.
Tapi diorang dah generate this based on your actual plan punya system lah kan?
So Excel tu masuk actual plan punya all the heat exchanger in temperature, out temperature, lepas tu dia generate this curve.
Bila dia masukkan temperature tu terus generate the curve.
Terus generate the curve.
Lepas tu dia tap in ke tak ini apa tu macam yang Zufan kotak-kotakkan tu.
Dia tak explain. I think dia assume semua orang faham kot.
Dia assume semua orang
Yelah,
faham.
tapi kalau pun faham, still tak tahu location tu kan. Exactly dekat mana heating medium tu. Dia tak tulis lah.
Tak tahu.
Kalau yang you cakap within process yang pocket ni, so that line exactly the line konon kalau macam yang ni from 160 to 150. So memang there's a stream with that condition exactly lah.
Betul. Dia ada.
And vice versa, dia punya yang kita nak exchange kan ada dari 132 ke 150.
Dia ada. Tapi where exactly? We have to go back to the table tu, mana tadi table dia? Table ni lah. Mana table tadi?
Excel tu.
Table ni. Jadi that 160 70 tu ada sini ya, di stream dia. Ini dia dia on that curve, it's going to be 160 kan, karena kita turunkan dia by 10 degrees C, going to be 160 degrees C. Terus yang heat yang stream yang kita mau increase to 140 degrees itu dia ini. Ini ada deh. Dia ada. Jadi so it can give like an indications, but to be precise where we will go to the grid diagram, because then we can see it clearly. Yang di table ni kita agak-agak aja, macam si Jam tu dia buat dan agak-agakan. Yang last meeting kalau tak salah, yang data I can exchange heat from here to there, so dia agak-agak macam dari sini lah. Macam dari sini. Tapi this can help as well, but the better way is then to go to that grid diagram I will show in the next sessions lah. it will be clearer because then we have this pinch point already there. So this pinch point is already there. So then we can see, because there is also another rule that we cannot violate, yeah, to design the heat exchanger. But that is for the next session. At least for these sessions, we can understand how this curve is being used to define the required utility levels, and also if we have already existing utility levels, yeah. Now, macam we have now already this utility criteria. So in this utility criteria, what I want them to have, yeah, what I want them to have is that they map this, yeah, because this then from the plant data, yeah, that we do, and then they map that utility criteria level. So we have, for example, utility criteria has this 160 degrees C, and then 160 degrees C goes to this plant with this amount of energy. Yeah. So I want to have that information here in this GCC, so that we know this is then the current informations. And then if I do the theoretical part, so say I only have like 160, 200, and then maybe 120. So if I have these 3 stream levels, can I rearrange the current situation so that I can maximize minimize the whole cost, for example. Yeah, so we have the existing situations, and then we can have the ideal situations, and then we can then find a balance where we can go on how much we can go, that kind of stuff, which I don't see now from KBR. Dia buat squat-squatty kan? Dia buat squat-squatty je ni kan, yang steam level ni kan? Dia tiba-tiba 600 pula, ada pula 150, 250. Ya kan?
Tak, yang 600 tu fuel, tapi on the steam dia pakai the actual steam available kan? Macam ke dia letak je nombor tu? Like
kalau yang saya faham dia letak je, karena kalau saya tengok kan Excel file tu dia beza-beza kan, different plant dia different pula steam level dia.
Patutnya sama je sebab it comes from the same source kan?
Iyalah.
Dia orang terbuat yang design dulu ke tak, ke dia terus
design dulu cuma
adalah design.
On the that one is on the heat exchanger side lah. On the utility side tu tak, tu lah macam nak kena check balik hari tu dia letak macam they just put a fixed number. They don't use the actual number.
Jadi orang pelan pun tak tahulah kan, ini sejak bila kita ada steam level 120 kata gitu. Yang last kali tu dia letak boiler feed water 120 degrees C as the hot utility. Kalau dia salah codingnya dia kurang betulkan.
I lost dah masa tu, dah tengok. Tak apa, nanti tengok balik yang tu lah. Sebab nanti they will present that to the plant also. Tengoklah macam mana dia present to the plant nanti. Is it going to be any clearer or is just, tengoklah.
Interesting dia. How they.
Cuma tu lah because they are doing it for individual plant, but I don't know how they are going to optimize for the entire
KPC.
Is it possible or macam kena tengok each plant satu-satu?
Possible lah. Dia dari sini dia tengok. Jadi each plant tu they have their own grand composite curve kan. Nanti dari sini grand composite curve nanti kita extract data lagi, itu next session pula kan. Kita extract data ni, jadi kita ada namanya macam side composite curve. Dari side composite curve tu kita akan compare dia dengan the current existing utility plant tu tadi tu. Dia level steam utility level ini sama ke tak dengan yang sekarang plant tu distribute. Dari situ kita nanti boleh tahu nampak. Okay, so we are now over consume steam at 150 degrees C katakanlah. So we better use, because there are some process that can use 120 degrees C steam. So we better maximize that first before we use the higher temperature level. Itu nanti kita boleh nampak. Untuk yang total site.
Alright. Okay.
Tapi kalau ini dia tak explain betul kan, kita tak faham, nanti yang ke depan nanti pun sana kita tak faham juga lah tu. itu takut saya.
Itulah, faham. So, nanti tak boleh nak challenge lah kalau kita tak faham kan.
Betul. Nanti kita ikut aja perkata dia kan.
Okay. Sorry Zulfan, have to cut you short for today. Nanti kita sambung Jessica okay? Faham tak?
Faham. Okay. Boleh ya? Boleh.
Ya, tak faham, just ask me.
Okay. Thank you.
Hari tu Jessica buat 40 card. The Excel tool tu Jessica dah buat 40 card hari tu. Try to tengok balik lah Jessica and fahamkan apa yang you buat tu.
Okay, boleh.
Ya, betul. Just try see if you can understand it, and then if not then we can always discuss.
Okay, can.
Okay, thank you Zulfan. Nanti kita arrange next one
Betul. Okay, thank you.
Thank you.
Thank you Dr. Zulfan. Thank you everyone.
Okay, bagi tengok.